And we first started talking about 3.0, I guess it was about 5 years ago. We were early on in the 2.0 version development, and we could already see that there were some limitations coming up in the code that at some point were going to have to be addressed. Some of those were going to involve more of a code change than we were just doing in our incremental 2.x version changes.
Much of the core framework has been completely redesigned in CONVERGE 3.0. There is no case that isn't significantly impacted by it.
Memory savings in 3.0 are mainly attributed to three different strategies. We have targeted three main parts of the code, namely the solver, the surface, and the mesh. In previous versions of Converge, certain information was stored redundantly. This used extra memory and required frequent copying of the data, which affected the runtime. We have removed these redundancies and streamlined the storage by utilizing new and better data structures. For most cases, this reduces the memory and reduces the runtime as well. For the second strategy, we have changed how the surface triangulation is stored. Previously, every core or rank stored an entire copy of the surface triangulation. For cases with very large surface files, this became a limitation. Very little memory was left for the solver and the mesh because most of it was consumed by the surface file. Now we are taking advantage of a new feature in MPI called shared memory. This allows all the ranks or cores to store and share a single copy of the surface triangulation. Shared memory is also used while mapping or restarting a simulation to reduce the memory load at startup. Our third strategy involves the mesh. In previous versions of Converge, every rank stored an entire copy of the octree down to the parallel block size. The limitation was that as the number of cores was increased, so did the memory. Hence, it did not scale well. We rewrote the mesh code such that we do not have this limitation. Now, every rank only stores the mesh or the cells it needs and nothing at a global scale. Our users can increase the number of cores for a simulation and expect memory per core to be less.
Scaling in Converge 2.x was limited in two main ways. First, the parallel block structure severely limited our ability to evenly distribute work among processes, especially in cases with highly varying embed scales. Second, we required each process to have a coarse view of the entire computational domain. This meant that at high core counts, our memory requirements became untenable. For Converge 3.0, we have completely rewritten the parallel mesh data structures in order to allow for an arbitrary partitioning of cells. This allows us to have a good work distribution, regardless as to the number of embed scales, AMR levels, base grid, etc. Additionally, we have removed the requirement that each process has a coarse view of the entire computational domain. This allows our memory scaling to match our compute scaling. This will help users whose cases are memory limited. The major difference is that load balance is now done directly on the mesh instead of on the parallel block structure. Additionally, we allow for automatic load balance detection, which means that the case is well balanced for as much of the run as possible. With these changes, we are seeing a significant improvement in scaling. Our previous recommendation was 50,000 cells per core, but in Converge 3.0, we are recommending as low as 3,000 cells per core, assuming that you are running on InfiniBand. Users will now also be able to run many different embed scales, as well as larger levels of adaptive mesh refinement, allowing them to capture more flow features without adding cells where they aren't needed. Additionally, users will be able to take advantage of large core counts in order to reduce the per core memory requirements.